Let's continue our discussion of two sample testings, but this time let's make the supposition and let's add the criteria. Last time we supposed that our data came in pairs. There was sort of this before and after scenario. And so even though we were talking about some time differences, we had the sense that there were some different, there were the same people across the rows. If you look at the data we look at today, you see that there are no such comparisons possible. One group is definitely different, bigger, longer than the other one. This is the perfect example to talk about what we would call independent data. So I haven't written this on the board here, so I probably should. Independent data is very much different from the pairwise data, because in the pairwise data we suppose that each of our rows was linked. And so we did our calculation. Essentially we simplified the problem, right? We subtracted, and this created a new column of just the differences, and then we just did an old school t-test. Now, if we assume that there's differences between the columns, we have to make some checks. First of all, between column 1 and column 2, there can be no connection. When we do independent data, they must be perfectly independent. So we don't dare have any overlaps. The formulas and the models we're using aren't set up to cope with any sort of overlap. So things to watch out for. I worry particularly about medicine, because of course we're always extra careful there. Suppose you're doing some tests and you want to compare your hospital to another hospital for, let's say, staph infection, just to randomly grab something. It would be very important that you had completely independent samples. That's very easy to do, perhaps, if your hospitals live in different states. But if your hospitals are right next door to each other, who's to say that in the week that you grabbed your data, that a patient wasn't in this hospital and in this one, let's say the emergency room twice. And obviously I'm not a doctor, so I don't exactly know how these things work, but something like this is conceivable. So you would need to make certain that you didn't have any matching data pairs in your samples. So for example, when I do this calculation of comparing face-to-face versus online for midterm scores, it's very important that I'm comparing from class in the same semester, because I know that our registration system won't allow students to sign up for both face-to-face and for online of the exact same class. This would very much not work if I wanted to sort of have a competition between me and the English department, because very much so, a student could be in English and statistics, and we would no longer have that independent samples. Notice in that scenario, nor would we have pairwise samples, because not every student in an English class takes my stats class. So as we're looking at these sorts of things, realize that again, very much we're in a what I'd call an intro stats environment. Last time we talked about perfectly paired data, this time we're talking about perfectly separate data. Don't let the formulas over here fool you. Ignore this for a second. Let's focus on this column. First of all, notice the same 5 steps that we do for hypothesis testing as always. We need to talk about alpha, the null hypothesis, and the alternative hypothesis. We maybe need to jazz these guys up just a little bit and talk about not mu d's anymore, but rather mu1 minus mu2, mu1 minus mu2. But other than that, same 2 things. And of course, I guess 3 things, right, for also alpha. Calculate the sample test statistic, calculate the p-value. If p is less than or equal to alpha, reject. If p is bigger than alpha, don't reject. And then interpret. So what's different? Well, the difference is this. When we had perfectly paired data, like we had last time, we had those dependent samples, we expected some sort of links between our data because we actually had something linking them. And consequently, we were only going to talk about a scenario in which we had only sample data, because we were looking at the 2 samples. Basically, we had this sort of secret guess that because these were the same people, we didn't really need to worry about certain considerations with, let's say, sigma. We didn't talk about that for that type of example. Here, when I have perfectly separate data, it makes a little more sense at this stage to introduce something that talks to us about either sigma known or sigma unknown. So notice we're once again up to two formulas, and of course we could even do one for binomial, right? The P, percent success and percent failures. But maybe it's easier to focus on these two. Again, of course, as almost always, for two-sample testing, as usual, the z-test where we can use the normal distribution, capital N, is maybe very, very less common than the other case. This is perhaps more likely that we would like to talk about the student t-distribution because we're going to have our sample data, of course, and this means that always automatically we have our sample distribution for free. Let me make sure that I've got my calculation going up here because I have a limited desire to enter these numbers into our calculator for a second time today. You've already seen it in the last section. So as we're taking a look at this, notice that we've got two possible ways that we could calculate our sample test statistic. Either we know sigma or we don't. If we don't know sigma, we know we're using the student t-distribution. When we use the student t-distribution, we know that we're going to have to talk about degrees of freedom. As long as we've had just one single row of things, degrees of freedom was easy. It was n minus 1. Now we've got two rows. And even more importantly than the fact that we've got two rows, notice these two rows are different. One's longer and one's shorter. Now you know that degrees of freedom is helping us calculate, essentially, think back to confidence intervals, it helps us calculate a range for our confidence intervals. Well, if we have more degrees of freedom, that range gets tighter. If we have less degrees of freedom, that range gets wider. So, if I picked this number, maybe my degrees of freedom would be very small. If I pick this number, it might be a little wider overall. Once I calculate it, if you can, think back to a confidence interval. Obviously, we would like to take into account the fact that probably the true answer for degrees of freedom needs to consider these. There's two different ways that statisticians consider this. One's I would call the old school way, and one's the newer, maybe more accurate way. So let's talk about both of them. And then in different cases in this class, maybe we'll do different ones. So going back, again, thinking of confidence intervals, if I calculated the x bar for this and the x bar for this and calculated a confidence interval around them, I would expect my t-test, that multiplier for standard error, to be a little bit tighter confidence interval here because I have more data. And we always know the more data we have, the more accurate our projection, our estimation, our inference onto the population is going to be. Here, because I have fewer data, we'd have to get a little wider to still get ourselves, let's say, with a 95% confidence level. That means if we want to be conservative when we're comparing the two to each other, we'd like to make sure that we don't accidentally get wider than we should, right? We don't want to get more degrees of freedom and accidentally think, oh, well, maybe I've got a very accurate level of data. So one option to calculate degrees of freedom, and this was the first one, and I think maybe it makes the most intuitive sense, just thinking about confidence intervals, is you take the number of terms in your first column minus 1, the number of terms in your second column minus 1, and you take the smallest of those two values. So I've used a minimum function here. In that case, we would look at this column and this one. We decide this one is shorter, and we'd say 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 minus 1 is going to give me 8. And we would go with 8 degrees of freedom. That's the smallest degrees of freedom that makes sense in this problem, and so we're going to have the widest confidence intervals possible. And you should have the instinct that if we go with the smallest degrees of freedom, we'll have the widest confidence intervals. Maybe our confidence intervals would be too wide. Maybe we're going to be too likely to not reject the null hypothesis here. However, we have the converse sense that if we went with what? This is 13 minus 1, we went with 12. That might be such a higher level of degrees of freedom than the right side has that we would have shrunk our confidence interval too narrow, in which case we would be too likely to reject the null hypothesis. And so we'd like to normally find, maybe you'd think we should find some sort of balance between the two. And we can. If we're talking about balance, there's a couple different ways that people did it over the years, but most recently what we have is Satterthwaite's formula, and I don't know if I can pronounce that word quite correctly, but Satterthwaite, it sounds like I can't talk. And this formula takes into consideration three things, and it looks very complicated, but don't worry, we'll always use technology to calculate that for us in this class. It cares about, of course, the number of terms, but it goes a little bit deeper with degrees of freedom and also looks at, notice here, the variances, that's standard deviation squared. It cares how turbulent each of our columns are. It compares and contrasts that with the number of items in each column. And so if you just look at this formula, don't calculate it, just look at it and see what are the pieces it asks for. It asks for how many items we've got in each column, because of course the more we've got, the better. And notice we always divide by the number of items. And so that tends to make this overall calculation, particularly down here, notice when we get this out, it tends to tackle this and say, okay, this lets me understand if I get bigger a number of items, I'm going to be dividing by, well, smaller things down here, right? And so when you divide by smaller things, that's making this denominator overall here smaller. And that makes the whole terms of degrees of freedom bigger if we hold everything else fixed. Because, well, there is one here, there's two of them here, and they're still being squared, right? It also, though, takes into account the amount of variation, the amount of turbulence in each column. And it creates ratios to compare those with that as well. And that's the sense that if this column didn't have all these different numbers, but instead kept on saying 0.55, 0.55, 0.55, 0.55, 0.55, 0.55, 0.55, it wouldn't matter whether we had 13 or 50 copies of just one number, let's say, and I just gave the example of 0.55, you would say, well, forget degrees of freedom. I know exactly what the confidence interval is. It's 0.55 and nothing else, because that's all this side does. So when you have small variance in a particular column, you would like to have a larger set of degrees of freedom. Again, start to create this balance here where you look at the pieces separately and you also put them together and say, well, together how much variance are we kind of talking about here? So this formula calculates degrees of freedom for us in a way that allows us to say how turbulent is our data, as well as how many data points do we have. So, maybe data just looks turbulent, but if we have more data points, that makes us feel more confident. So this formula is a more accurate way to calculate degrees of freedom. Depending on how some people calculate it, some programs calculate, they either truncate, so they forget decimals and they just go down, so let's say we had 17.9. It would just call it 17 with truncation. Sometimes a lowest integer step, because you won't want to round up to 18, because again that would be too many degrees of freedom, which would give you too narrow of a confidence level. Don't be shocked if the more advanced degrees of freedom formula give you a degrees of freedom bigger than any single column. It would do that if it looks at the overall variance and decides that it can actually squeeze a little more out. This degrees of freedom gives us a much more accurate t-test lookup, and if we have a much more accurate t-test lookup, well, that's going to give us a much more accurate confidence interval that will be more likely to do exactly what we were hoping. Again, perfectly fine to use the degrees of freedom, just n1 minus 1 versus n2 minus 1 and pick the minimum. That's been accepted for many years. Watch carefully on your homework. If it asks you to use Satterthwaite's degree formula for degrees of freedom, you're going to want to use that. And we'll talk about the technology behind that, maybe in a technology breakout video. Or read your book and it will explain how to do that as well. So, let's take a look now at this problem. Here, I have midterm scores from face-to-face versus online. And as we look at the midterm scores from face-to-face versus online, we might like to start to calculate some things. So again, I've calculated this up in Excel. And that means I've already calculated some of the things. Again, you could just as well type these data into your calculator and run that analysis. So I have 0.61 for x1 bar. I've got 0.61. And I'll put little wiggly equals brackets here. And I also have S1 of 0.16. Conversely, over here we've got x2 bar and S2. And For that I have 0.67 as well as 0.17. So what we notice is that there's a little less deviation in our face-to-face group. There's more consistency in our data because we have a smaller standard deviation. We also notice, though, that overall the average is higher online than it is face-to-face. Okay. So now we've got those pieces. The first question we want to ask ourselves is, one, we would like to compare these data, because what's the question? The question is, what's better, an online or a face-to-face class? Which one has a higher thing? And we look at this and say, oh, okay, this one looks higher, but again, it's not all that much higher, and it's time to do a statistical test. Because notice the deviation. Plus or minus 16%, plus or minus 17%, that's a lot of turbulence. You don't want to just say, well, that 6% means something. That might be well within the turbulence range if we don't do a little more accurate calculating and do these tests. Okay, so next thing that we have to do. This looks like we've got two different samples. So I look at it and say, yes, we do have two different samples, and yes, we do want to do a hypothesis test to decide who's better. Someone should probably say something about alpha. And again, for education, maybe I personally use an alpha of 0.1. I've seen as high as a 0.2 in some literature and research. Okay. So using this, we would like to do a hypothesis test. This is definitely two samples. So we think of our two sample techniques. However, looking at this, we also instantly decide this is not a pairwise sample. Our data aren't paired. It's not the same student in row 1, and by the time we get down here to, I don't know, row 11 or so, we don't have any sorts of pairs to make. All right. So now we have to decide, well, what are we going to talk about with step 1 here, and also, are we thinking that we're going to be using a sample test statistic involving normal or t-tests? Well, you have to look back at what I've given you. For sure, we're always going to have these. You can't get around that when you have sample data. The question is, do I happen to know population measures? And in this case, I haven't given us population measures. So we decide that the correct thing to do is going to have to be a t-statistic because we don't know sigma. I would have to tell us both sigma 1 and sigma 2. And since I've only recently started teaching the online version of this class, I've generally taught face-to-face versions because I'm physically present here at this college, I don't actually have population data for the online students yet. You could probably look it up and request it, but I haven't. And again, it's much more normal to not know population data. I could actually tell us sigma 1. I know that. I've taught this for at least, 5 years now here at this school. So I'm pretty solid on the population sigma 1. It's the sigma 2 that I just don't quite have enough data yet to have any confidence on. So we're going to have to say, let's wait, and we go back to this t-test idea. Okay. So first of all, alpha was 0.01. Excuse me, alpha was equal to, not 0.01, 0.1. 10%, not 1%. And then sigma is unknown. So we're going to go with this t-test. We have to talk about the null hypothesis and the alternative hypothesis. The null hypothesis in this case is going to be that the difference between these two is 0. Again, just like we did last time, it is entirely possible that I might have run the calculation with some number other than 0 here if I often think that I expect to have some sort of difference between these. But in this case, since this is a bold new foray into the online scenario for stats, I normally teach business courses online and do online stats consulting, but anyway, this is going to be a null hypothesis of 0. And now we have to pick the alternative hypothesis. Of course it's going to be mu1 minus mu2, and of course we're going to have a 0 here, but we have to decide less than, bigger than, or not equal to. Again, this is a decision that comes from my data. If I simply think that the alternative hypothesis is there is some difference, then I will go with does not equal. This side is smaller than this side, so when I do a subtraction from 0.61 minus 0.67, I would expect a negative number, which means negative numbers are, in fact, less than 0. So my options here could be a left tail test, or a two-tailed test. These are the two ones that make sense. In this case, I'm going to go with a left-tailed test. Alright, so we've decided on a left-tailed test. Again, carefully read every word problem you're given. You will know if it wants a left-tailed test because it will say words like less than, smaller than, littler. And you'll know if they want a two-tailed test because they'll say words like these two categories are simply different. So they use words like different or not the same. They won't describe one as bigger or less than the other. That's part of the initial set of hypotheses that we develop. I think students often have trouble distinguishing between left-tailed and two-tailed or right-tailed and two-tailed. For sure, you would not see a right-tailed test with this data because 0.61 is smaller than 0.67. A right-tailed test would have made no sense and no one in their right mind would have ever come up with that one. Alright, next we have to talk about sample test statistic. And that means we're deciding here, because we don't have sigma is unknown, we're going to go with a t-test. So t is going to be approximately equal to, I'm doing wiggly equals. In real life I would plug this t-score into, I wouldn't round, don't do rounding, but just so I can fit this all on the board, I'm going to go ahead and round for this example. But again, in your homework, do not round. Do not round until the very end. That way, when you plug it into your homework and it does the calculation, and the homework doesn't always accept a single answer, it accepts a little range, but that range will only probably take your answer if you go ahead and don't round at the beginning. But I'm rounding just so I can fit all these numbers here on the board. So I've got for x1 bar 0.61 minus 0.67 minus mu1 minus mu2, which we're supposing in the null case is 0, so I do minus 0. Of course, that doesn't do anything there. Alright, on the denominator, I've got the square root. Again, do not round. 13 and 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13 for n1 and n2. And of course, I also calculate s1 and s2. Again, I rounded 0.16 quantity squared, 0.17 quantity squared. But again, you would not. So we've just gone ahead and plugged in our x1 bar and our x2 bar. mu1 minus mu2 is going to be 0. Sigma 1's quantity squared, sigma 2 quantity squared, 13 and 9 for n1 and n2. Again, I'm making the point that in real life, when you did this, don't round. I'm rounding these just so that we can keep this all nice and tight on the board, and I can actually show you kind of where I'm plugging in my numbers. And we got those numbers again from here on the side. So now we're ready to calculate the t-statistic. As I calculate that t-statistic, go ahead and plug this into our calculator. I'll use the fraction bar here. On top I'm going to get 0.61 minus 0.67. I'm expecting a negative number there for my t-value. On the denominator I'm going to go ahead and hit second the x squared, which will give me a square root, and then I'll use more fraction bars to get 0.16 squared over 13, as well as fraction bar and 0.17 quantity squared over 9. And here in this case I am getting 0.8336 for my t-statistic. 0.83. Maybe we would normally round to 4 or 3 decimal places here, so 36, so 4. Over here I have my Excel program up, and it's gone ahead and told me that the t-statistic I was rather expecting was negative 0.808. Oh yes, I should write the negative here, shouldn't I? Notice the difference there. 808 versus 834. The 8's right, but we're off by what? 2, almost 3%? At that last term there, so be careful when you round. That's the difference between rounding and not rounding. This probably won't make us change our decision in terms of reject or not reject the null hypothesis, but still, you should be careful. And of course, that 808, even if you typed in these numbers, you might not get them, because I also actually rounded these a little bit. I generated the data out to a couple more decimal places, and of course I didn't truncate any of that in Excel. So again, watch that rounding carefully. If you typed in, maybe 3 decimal places here instead of 2, you might have been accurate to the first 2 points. You always want to watch that rounding business, and that's why I always suggest Don't round till the end, and I admit on our calculator that's a bit of a pain, which is why I always recommend Excel, of course, because then you don't have to round at all as you're doing these calculations. Actually, I recommend things besides Excel, but anyway. So this is our t-statistic. We are done with step 2. It is now time to go through step 3. We have to calculate our p-value. Since it's a t-statistic, we would like to look this up on the student's t-distribution. We are looking for a one-tailed test because we've chosen a one-tailed test. And again, we could use technology to look up a specific example, or I could go ahead and look at my chart and find a range, right? And as I look at this chart and find my range, I'm looking for, let me go ahead and find the student t-distribution. We need to know degrees of freedom. I'm suddenly realizing as we calculated this. So degrees of freedom. Our options. We could take the minimum between 13 minus 1, which is 12, and 9 minus 1, which is 8. So we would pick 8. 8 degrees of freedom is one option. Alternatively, we could use Satterthwaite's formula. And if we use this formula, we would calculate out something. Remember, it would depend on not just the number of terms in each column, but also the variances. Excel has told me that Satterthwaite's is giving me degrees of freedom. We'll put a little s down here for degrees of freedom under Satterthwaite's. Of 17. I can go ahead and truncate some things. Notice the difference. 8 versus 17. Remember, in the student t-distribution, smaller degrees of freedom give you a wider confidence interval. So the difference between 8 and 17 is actually quite a bit in this case. That will give me a much more actionable test. You might ask yourself, why did we use the minimum here? Why didn't we go for the max? Because even 17 is even bigger than that 12. The answer has everything to do with the variance. This formula also takes into account how much variation we had in each column. And so if there had been more variation, if the variation had been different than what we had, we might have expected a different answer out of Satterthwaite's, and that would have given us a smaller number here. Satterthwaite's tends to be a very accurate way to calculate degrees of freedom as long as we have at least 5 terms in each column, which we do here. So Satterthwaite's becomes pretty a decent way to calculate this, and certainly, since I like to be more actionable rather than less, I prefer to go with the 17 rather than to go with the 8. Either one would work, and quite possibly either one will lead us to make the same decision. In fact, let's look. If we go with 8, we're looking up a t-value of negative 0.834. So we chop off the negative with t-distribution when we look up in our chart. So we're going with 8, and we're looking for 0.8, and that's living in between these two. We go up and look at our one-tailed area, and we get between 0.125 and 0.25. So my p-value, 0.125 and 0.25 for one-tailed area. Notice that's the same region I would have been in if I had calculated without rounding. Because without rounding I was getting, what, 0.80 something, and here I got that 0.83. Either way I would have been in the same place and looked up here. We were comparing this to an alpha of 0.01. Not 0.01, 0.1. Contrary-wise, what if we had picked degrees of freedom equal to 17? Well, then I'd go down on my chart to 17, look across, and notice, even though the range has tightened up a little bit, I still haven't, with 17, got myself with that 8 in any particularly different place. I still have the exact same range there, which gives us the exact same set of decision criteria. So you can have some confidence that for most of the intro kind of calculations that we do, minor differences in degrees of freedom probably isn't actually going to change our decision all that much. So if we're just looking at the decision we're talking about at the end, well then, we've got everything we want here. We're going to make the same call either way. The closer your p-value is to alpha, the more careful we have to be, right? Here's what I really want to focus on. Look at this. The difference between these two columns was only 6%. The usual amount of variation between them was 16 to 17%. The turbulence in each column was so much that that teeny difference between them isn't really going to make all that much of a difference. Because look here. P is bigger than alpha. P is on the right, alpha is on the left. P is bigger than alpha. That means we've got this. P is bigger than alpha. Don't let the mirror images of the inequalities fool you. The bigger part is focused on the P. The bigger part is focused on the P here. This means we do not reject the null hypothesis. So step 4, we do this. Do not reject. Which means step 5, when we interpret, I would say there is no evidence. No evidence supports a difference between classes. Which means you can take an online class and you can take a face-to-face class. Don't drop your face-to-face class because you say, oh look, the online people got 6% better. That 6% doesn't mean anything. There's too much turbulence for us to make any confident call and say, you know, not everyone should go online. Conversely, maybe this isn't really low, or maybe secretly the real, because remember we're talking about confidence intervals, it's possibly the real actual higher score does come in a face-to-face environment. But again, at the moment, with only 13 people on one side and 9 on the other, we don't have enough information to make any sort of call. These were based on the online and face-to-face midterm scores that we were looking at. I didn't actually grab anyone's real numbers as usual. I took the data that I had and I regenerated some numbers that would give us the same conclusion. The fact is I can't say whether face-to-face or online is better. In fact, I've got some evidence that supports no difference. We're not rejecting, I should write this, H naught. In all likelihood, it entirely depends on not any delivery of venue. In fact, much more advanced research than just comparing two random midterm scores suggests that midterm and face-to-face is less key than, of course, you. You decide your own fate. Much like in Terminator, it's your call. You get to pick. It's all on you. Your teacher can motivate you maybe a little bit, and that's perhaps harder to do in a online class. A teacher can select a textbook, and maybe the textbook makes sense, or maybe it doesn't make sense as much, depending on people's different backgrounds. But the fact is, if you're excited and passionate and eager about something, you're going to spend a lot of time in it. You'll spend whatever time it takes to make it happen, and you can succeed no matter what venue you choose. Contrary-wise, if you're not very interested in something and you don't spend a lot of time in it, then it will never go quite as well. That's certainly been true in every class I've ever taken. The less I like a class, the lower my grades seem to be in it, because I'm like, yeah, I just can't do it. It's like, you know, some lower score is fine. The idea of putting an extra hour into it is just beyond me. Whereas if I decide that I find a class useful, if I know why I want to take it, then I start spending extra time. I start emailing that professor, going to office hours, whatever it's taken at different points in my life, until I finally learn how to make that happen. And I would say that one of the best things that I can tell you is book reading. Read the book, and read the book often. You read a textbook, I am always amazed every time I reread our textbook how maybe, so I don't want to say extra insight, because, you know, I've taught this for a long time, and of course I do a lot of statistics, but I always see something that the author said that seems like some sort of random sentence, and it's like, oh, actually this is quite brilliant. It's a good thing he's saying this, because this is what's happened. And it's a good thing that, I guess we've got 2 authors on most of our textbooks, and we've got a male and female author, so it's a good thing she's saying it with the parts that are written over here. It's very important to look through a text and read it many times, because the authors are usually, most people who write a textbook are pretty clever in their field. They have good things to say. I think sometimes the stress part is to look at it and say, well, it's not making sense to me right now, and that's okay. That's why you want to reread it, and reread it again. And after the 5th time you've read it, you'll be like, oh, okay. And then do it. Don't just read it, but actually do the examples. And once you've worked through the homework, then go and reread through the book again, because you'll say, oh, wait, that part on that homework that I was having trouble with, actually the author right here was trying to explain it. I just didn't understand enough at the time to get that piece of insight. So I think that's what we're looking for here. Things that you'll do in this section then, as we were talking about homework. Same 5 steps, sigma known or sigma unknown. We did an example where sigma was unknown because I hadn't said anything about population deviation. Normally, population deviation, if it was going to be known, would be included explicitly. Look in the problem, look and see if they say sigma equals. And I think as we're getting ready to be done with the initial intro to hypothesis testing, you want to be thinking about, if I look at a random collection of data and a description around that, some sort of word problem in front of it, around it, how good am I at deciding which tests to use? Can you look at a raw piece of data and say, you know what, this one's a confidence interval, not a hypothesis test? Can you look at some data and say, this is 2 sets of hypothesis tests, or no, this wants to be paired? So reread through the homework problems even, and say to yourself, how do I decide what we want done here? What words, what keywords flash in my mind and make me think this is interesting? I always wish I could get one of those cool, I've seen it before, it's like some sort of electrode helmet, and it tracks where your eyes watch and puts little dots. And you've seen it, you have to have seen it in some sort of news articles before. It shows that this part of our face is the place where we look at people, and then you look at this triangle around sort of your nose and mouth enough, and that lets you recognize one person from another. So I can recognize my mother by sort of the eye spacing, her nose, and her mouth, and that's kind of what instantly lets me decide mom, versus when I look at someone else and say, well, that's not mom, and so on. So I always would be very interested in looking at a word problem, and I see the places where I look versus where I sometimes think students are looking. Things that I always look for very, very fast in a word problem are, do I know what sigma is? Because so often that helps me decide some of my tests. And I always ask, when people try to use a z-score formula and they don't have a sigma, I ask them, what did you use for sigma? Why did that number make sense to plug in there? And then usually you get a sort of strange answer like, well, I just plugged some numbers in because I wanted to. So look for sigma. Look explicitly in there. When you're trying to decide left, right, or two-tail hypothesis testing, look inside the problem and ask, does it tell me about some numbers being less than things? Well, then you think left tail. Or does it tell me about some numbers being bigger? Well, then you want right tail. Or does it simply say, the hypothesis is that there is no difference, in which case you're thinking two-tailed, some difference. It has to be the alternative hypothesis. I think that's good enough for this section. We've worked through an example. We've pointed out the fact that if you round too early on, you're going to get some different answers, and you should be careful with that. So don't round till the end. I was able to safely round because, 1, I'm not plugging this answer into homework, and 2, I wanted to keep this a nice tight example on the board with just a few decimal points. But don't round until the very end, and then you can round to the 3 decimal places or so for a t-score as you're looking things up. We also talked a little bit about the difference between degrees of freedom, different ways to calculate it, and I said that at the least we should use 8 degrees of freedom for this example, but Satterthwaite's might give us a slightly more accurate degrees of freedom, which would hopefully be bigger than 8, which would give us a tighter confidence range, and thereby make us more likely to reject the null hypothesis. Even with a score of 17, we still saw that we weren't able to get a confidence level that was tight enough that made us decide that, we can reject the null hypothesis. So either way, we have to say in this case, take an online class, take a face-to-face class, it doesn't make much of a difference. Alright, but I think that's good enough for this section, so I'm going to let you go. you can study on that, and I will see you very soon as we start talking about some very interesting ways to not just interpret and infer some statistical data, but maybe to actually start to make some sort of prediction or projection on stuff. Be very, very useful and very real. Until then, be safe.